We're now going to go ahead and take a look at another type of discrete probability distribution. This one is called a binomial distribution, and we'll see what entails why we call it binomial. But again, that word "bi" meaning two. In our cases, we're going to be looking at situations where there's two possible outcomes. And so, in this first class challenge, this is really meant for a conversation in class and a review of past probability calculations. This idea of what is the probability that you could guess, right, on a multiple choice exam, right? If you have three, right, looking at this first situation, three questions, each have multiple choice questions, each have three possible answers, one of which is correct, right? Assume that you guess answers to four questions. So what we need to think about is you have four questions, you have a 1 out of 3 chance of being correct. What's the probability, right, of getting all four correct? Or what's the probability of getting half of them correct, right? So looking at this scenario to answer the question, we would need to use this multiplication rule. And you can see here, here's the probability that the first two guesses are wrong and the third is correct, right? You get the first one wrong, the second one wrong, and then the third guess correct. This is how you would calculate it, right? 2/3, 2/3, 1/3. Now, what is the probability of getting exactly one correct answer when four guesses are made? So you only get one out of the four correct. So the hard part of this is you having to analyze this question of the probability of one being correct really entails four different scenarios, meaning that you can get the first one correct and the rest wrong. You get the first one wrong, the second one correct, the rest wrong, right? And you could see this pattern. So there are four different scenarios, and that's what complicates why we can't just use the multiplication rule once. It needs to be done four times and then added together to get you a 32 out of 81 chance of getting just one question out of four right when you're guessing. That's why it's tough to pass an exam when you're just guessing multiple choice questions. Now, we'll analyze what we're going to learn is we're going to find a shortcut to do this calculation. Now, before we do that, let's go back to random variables. In this case, we're looking at a binary random variable, right? We're going to look at the possible outcomes. Binary meaning we classify each outcome into two groups. And statistically speaking, or scientifically or mathematically, what we call those two groups is success and failure. Success is the thing that we want to see, that we're checking the probability for. Failure is the thing that's not what we want to see, or the thing that we're checking the probability of. And so for a variable to be binomial random variable, it needs to have these two outcomes, the variable for that situation. We also need to know that the outcome, right, when we're looking at the outcomes of this variable, that the outcomes are independent of each other, that whatever the outcome is, right, and whatever we're trying to measure in this case, that it doesn't influence the other. Like in this situation, the outcomes that you're correct or wrong. And so whether you're correct or wrong has to be an independent event, meaning that you don't have any other, no one's influencing your choice of answers, you're not cheating, right, those types of things. And then the third one, this idea of when we're analyzing a binomial random variable, that the number of outcomes is fixed, right? The number of trials is fixed. We're going to analyze this for 10 times, 20 times. It's not an indefinite situation. So we sometimes refer to this as bin. You got to check the bin. This is different than what we learned in histograms, but binary, the variable needs to be binary, it needs to be independent, and also the probabilities are identical. And the number of trials, the number of observations we're looking at is fixed. It doesn't change. And here's a scenario you could read yourself, really is what is success? Again, it's the thing that we're looking for. And you can see how we define success and failure in this example here. If we're trying to measure, right, in a classroom, if someone's a first generation student or not, meaning that they're no one in their family graduated college, right, we would consider a success for each of the following responses. If the mother said no, the father didn't go to college, right? If one of them went to college, right, as we look at this here, again, looking at what is success, anything we're looking for. We're interested to see how many students are first generation students. A survey question is asked to students which of their parents have attended college, right? What would we consider success for each of the responses? So the idea, if the mother went to college, right, that's a failure. If the father went to college, that's a failure in terms of someone being a first generation student. Neither went to college, that would be success. That's a first generation student. If they both went to college, we consider that a failure in this case. Failure in this is one or both parents attending college.